So, we will skip the second option for now and discuss the moving average model first. All right. So, on the screen you see the general expression for a moving average model of order m, and as you can see that there are m terms now and there are m unknowns plus sigma square e. In total you have m plus 1 unknowns to be estimated from the data, all right. And again here you should keep in mind the perspective is that the time series is purely being explained by the shock waves alone, not by its past. At a later stage we will show the equivalence between this representation and the counterpart, the autoregressive model, where the time series is explained purely in terms of its own past. We will show that they are equivalent, but right now let us again focus on the moving average model, and the transfer function operator is fairly straightforward to see. Now, from a forecasting perspective, once again Ek is your unpredictable component that keeps flashing at you, and now we talk about the conditions or the impositions that we have to place on the model so as to guarantee stationarity. But since we are starting anyway from a linear random process and throwing off all those coefficients that we assume to be 0, we should not expect any major requirements coming into forth as far as stationarity is concerned. If you go back to the general linear random process, what was the requirement for stationarity? We said that this sequence here, the impulse response coefficient sequence should be absolutely convergent. Now that is readily satisfied. Now we replace this with Cn. That is readily satisfied. It is a finite number of terms. It is satisfied as long as the coefficients are bounded. And it is a very mild assumption. Okay. So you should keep this in mind. The moment we move from this infinitely long the stationary linear random process to now this finite impulse response model, the stationarity requirements are not so binding. In fact, now you can view the linear random process that you have been seeing as a moving average process of infinite order, right. The earlier one that we had written, you can write it as MA infinity, that is how it is referred to as in the literature many times. This is MAM, and the linear random process that we have been looking at is MA infinity. But when you move from this finite impulse response model to infinite impulse response model, you have to worry about this restriction, whereas it is not present here. It is, but you know it is easily satisfied. Okay. So, just as a tidbit, the MA process of order m is also known as M correlated process for reasons you know already. The ACF of this process dies exactly after lag m. So, the correlations only last up to lag m, and therefore it is called an M correlated process. So, we will quickly breeze through the ACF of MA process, and the reason we are doing is because for a given process I would like to know whether an MAM model is suited. The series is not going to speak to me and say, yeah, here is the model. I have to figure out, I have to calculate some measures or metrics and figure out what is the nature of the underlying process. And we know already, at least from theory, that if the ACF of the series dies exactly after some finite lags, a plausible model is an MA model of order m. So, good, which means we not only have a model with us which is workable, that means I can estimate a finite number of knowns, finite number of constants and sigma square e, but also a signature that tells me when this model is warranted. That is the most important thing. Making decisions on the model structure, the type of model and so on is what actually eats away a lot of your time in time series modeling. All the other things, yeah, there is data cleaning, but once your data is clean, most of the time is spent on determining the type of model, and a lot of times you do end up with multiple models competing for each other. Then you have to conduct an election, right, and take a poll. You do not ask people around, okay, that is not what I mean, do not do that during the exam. But there are information theoretic measures, for example, that will allow you to do that, which will allow you to tell, it allows you to determine which model is suited when you have a bunch of models competing for a given process. But right now let us say that at least now we have this ACF telling us whether an MAM model is suited or not, right. And just we have seen this already, I am just going through this for the sake of completeness. The ACF of an MA1 process we have seen many a times and probably a lot of times thanks to your quiz. So, we will skip, and we have also proved through the use of autocovariance generating function that the ACF dies off exactly after M lags. For us right now what is more important is mapping the ACF with the model parameters. We know that the ACF tells us not only the fact whether an MA model is suited or not, but also what is the order, at least theoretically. Now, having determined the order M, so now when before I begin I do not know what is M, whether this model is suited or not. So, I look at the ACF, and if the ACF supports my postulate that there is MAM model, or it gives me substantial evidence, then I postulate this model, and the ACF will at that stage I do not know M, I do not know these constants, and I do not know sigma squaring, right. This is also unknown. But once I look at the ACF, I also figure out what is M. So, now the job in hand for me is to estimate these parameters and sigma squaring. Therefore, I need to figure out whether there is first of all a mapping between the ACF and the model parameters, and if that mapping is unique. Here again I have to raise that uniqueness issue, because maybe when I sit down to estimate these parameters, I may run into this non-uniqueness issues. There may be multiple solutions. We have fixed only one layer of non-uniqueness, there can be several layers of non-uniqueness troubling me. So, this is the second layer of non-uniqueness that we may run into. So, we have discussed this in a somewhat quick manner in the last class, but let us spend a bit more time on it and also formalize those results and the invertibility condition. So, if you were to go back again to this MA1 model, we have already seen that there are two solutions when I want to estimate the model. So, I want to know what is C1 given rho. We know that there are two solutions to this. It is not that always I will use this equation to estimate C1, do not get this into your mind, but this is one of the ways to do it. Now, what about other methods? Do they make use of this relation between the ACF and the model parameters? Not explicitly, but whatever you do, whatever you try to do, ultimately you will run into multiple solutions. For example, later on when we learn estimation theory, and we at some point we will learn how to estimate moving average models formally. This is also a formal way of estimating the moving average model, but using least squares approach, for example. This is not a least squares approach, this is called a method of moments, where I am forcing the moments that I am estimating to satisfy the theoretical equation. That is the idea in method of moments. But when we learn least squares, there also we shall learn that we would run into a non-linear least squares problem, not a regular linear least squares problem, which has a unique solution. A non-linear least squares problem has multiple solutions. So, this problem of multiple solutions will continue to haunt us whenever we deal with moving average models. The nice thing about moving average model is stationarity is not an issue. That means I do not have to worry about placing any restrictions on these coefficients. But somewhere I pay a price, and here is where one of the places where I pay a price, where I start feeling the heat. So, now I have two solutions as we discussed in the last class. If C1 star is a solution, then 1 over C1 star is also a solution. right. Two solutions are present, both are candidates, and I have to decide now which one to pick. And as we discussed in the last class, the criterion that we use for selecting this model here is forecasting, because ultimately I am going to use this model for forecasting, and I should select a model that will give me stable forecast, but it is hard to actually think of it straight away. You can't actually look at this and say you know, I know there must be an issue with one of the things, one may give me stable and the other one may not give me a stable forecast. It is not so straightforward, it is not as intuitive as I am making it sound. One requires some formal thinking. Maybe it could have happened that someone tried to use the other solution which is not so called invertible and got beaten up, and then come back to the desk and figure out, oh, you know, there is a possibility that one of these models can give me unstable forecast. But you know, maybe there is something else that has also happened. In any case, now we can ask what would happen if I were to use this model for forecasting. So, if I am given information up to k and I want to make a prediction at k plus 1, then what would I do? I would actually go back to my model, because I have chosen to work with an MA1 model. The forecast is C1 Ek. Strictly speaking, this should be expectation of Ek given information up to k, right, which is not 0. If you have any questions on that, you should ask. The unconditional expectation of Ek is 0, but the conditional expectation of Ek given all the information up to k, it is not a prediction, we call it as an estimate or a filter. This is not 0 because Vk and in fact Vk minus 1 both will contain information about Ek. So, I can leverage on that and make a better estimate, get a better estimate of Ek as compared to the unconditional expectation. So, the question is now, how do we recover this? And that is what we discussed in the last class. How do I recover Ek from the given information, and whether it makes a difference if I use C1 star or 1 over C1 star. And as we have seen in the last class, we had one perspective, but let us go through 2-3 different perspectives on recovering Ek from Vk. This is a simple way. What you see on the screen is a very simple manipulation of the difference, the equation that we wrote. Your model is Vk equals C1 Ek minus 1 plus Ek. This is your model, and what we want is an estimate of Ek. So, we rewrite this and just do some algebraic jugglery there, and straight away see that Ek is Vk plus some infinitely long summation. So, what this tells you in the first place is to recover the shock wave that occurred at kth instant exactly, what do you need? What does it tell you? Yes, you need the entire history, you need the infinite past. In fact, it should tell you, this is actually a very classical problem that you see in physics, like Big Bang theory. What happened at the time origin? What is it that generated what we see today? To be able to actually come up with what really triggered the universe, you need that entire history. Do we have that? We do not. So, it is okay, people will keep making guesses, some 1000 PhDs will be generated, then somebody else will come along and say, no, that is not possible, I have a better evidence today. You keep guessing, it is okay, chalta jayega, no problem. At least it is keeping people busy, right. So, it will continue to keep people busy, because we do not have any infinite history. So, this is only a theoretical expression which is useful. In practice, I do not have infinite history, right. So, we will talk about how to deal with the lack of infinite history and so on at a later time, when we specifically focus on forecasting. At this moment, what is clear to me is that if I want, even if I am given the infinite history, to generate a stable forecast, right. What we mean by stable forecast is the recovery equation should not result in an unbounded sequence, because Ek is stationary, that is a minimum requirement, and for that minimum requirement to be satisfied, the C1 has to be less than 1 in magnitude, right. The straight away tells me which I should choose. If C1 star is a solution and that happens to be less than 1 in magnitude, then I discard 1 over C1 star. But what is puzzling to us is, even though there is a series that must have come out of 1 over C1 star, I still have to work with C1 star. In the sense, let us fix some values here so that we do not talk symbolically. Suppose the solutions are 0.5 and 2. Suppose I have used, or the process is actually running with 2, the value C1 being the value of 2, I still cannot work with that value. It is a bit strange, because I am not working with the truth. In other words, I will generate a series out of an MA1 process using C1 value of 2, and I will give you the series. You cannot, even though you find that 2 is a value along with 0.5, you cannot work with 2, you have to work with 0.5. Why is that? Why are we running into this kind of a very enigmatic situation? Although you have managed to figure out what I have used in my simulation, you are still forced to use another value. In other words, you will not be able to figure out whether I have used 0.5 or 2, that is another issue. But even if you have figured out, that is in your set the true value has come up, you are being forced to use another value for generating stable forecast. What is the reason here? What is the prime reason I am being forced to do this? Sorry? You are already meditating, man, at an angle. They said tomorrow people will meditate, you are already meditating, practicing maybe. I do not know what is that asana called though. Slant asana maybe. That is okay, do not worry. What is the reason?
Absolute convergence of this.
Absolute convergence of what?
ACF.
Okay, let me ask you a different but a related question. Would you run into this situation if you are working with deterministic models? I will not cross the Lakshman Rekha. The font size is adjusted accordingly. Would you run into this situation with the in the deterministic world? Yes or no? Yes? No. You cannot go by my reaction, it is not Lok Sabha. In Lok Sabha only people go by reactions, go by numbers, reactions, need not by truth, by facts. Anybody from that hall? Would you run into this kind of a enigmatic situation, strange situation that you see here in the deterministic world? Who would like to answer at this wonderful hour of the day?
No, sir.
I was hoping you would say yes. Yes or no? In the deterministic world, would you run into this situation? Why? Why?
Because we know what is causing the input and output.
Ah, so the cause is known, right? Here, after estimating this model, I had this additional headache of going and recovering the cause also to make a forecast. Whether I am doing it explicitly or implicitly, you will see that this need of explicitly or this kind of an equation is not required in autoregressive models, because the autoregressive model is very nice. It directly models the series as a function of its own past, which is observed. Here the moving average model is modeling the series as a function of an unobserved quantity, unobserved variable, right. So, there is this additional responsibility of recovering that unobserved cause if I have to complete my forecast. Even in the autoregressive model, somehow if not that, something else will crop up. Life is not actually, so nice wherever you go. It is just that, here you deal with some situation in India, when you go to the West you say, oh, those problems are not there, it is so nice and so on. Over a period of time you figure out there are problems there also. So, it is a matter of what problems you are comfortable with, that is all. Life is all about where you settle, predominantly depends on what problems you are comfortable dealing with, right. Here if you do not mind running for the bus or something like that, and you love doing that, or you love facing all the kinds of problems that you actually love bargaining and so on, it is great. When you go to the West, there is no bargaining, it is boring, really boring, you can't really haggle around and so on. So, but there are other issues, it is so beautiful, just minus 20, you cannot actually walk around with your slippers of different colors and half broken and so on. I have also worn those, do not worry. You can't do that, right, and no jugards and so on. But there are other problems. Likewise, you see in modeling also, with moving average models, you may have some issues and you may not have some issues, while with AR models you will have some other issues and so on. So, the main problem here, the main reason as to why we run into this situation, where I am forced to work always with that model which gives me stable forecast regardless of what has been used for generating the series, is because the cause is unknown. If only I knew Ek, then automatically things are fixed. You see this here, but fortunately for us, we are using an equation that does not have sigma square E. We are very happy that we got rid of sigma square E, but the problem makes its way through in a different form. If you look at actually the estimation of moving average model of order 1, there are two equations, right. One equation is sigma at lag 0, which is sigma square V, is 1 plus C1 square times sigma square E, and the other one is at lag 1, which is C1 times sigma square E. So, perfect, I have actually two equations and two unknowns. But in going from here to here, I have gotten rid of sigma square E, and we are very happy about it. I can estimate C1 without knowing sigma square E, which will also be the case in autoregressive models. I can actually estimate the parameters without knowing sigma square E, then post parameter estimation I can estimate sigma square E. But even though I have when I have managed to get rid of sigma square E, it still makes its way, that is the fact that Ek is unknown. Imagine if Ek was known, right. If Ek was known, what would happen? Then I have to choose a C1 that exactly satisfies the other one, right. There are actually redundant set of equations then, but that redundancy will help me, correct. If I choose to work with the first one, what would happen? I will get 2, but it has to satisfy the second one. So, inevitably then I will have only one value of C1 and I will live happily with that. It is a fact that sigma square E is not known which is actually causing me forcing me to run into this situation. So, some thinking will really help you. In spectral factorization, we will see the same thing appearing in a different way. Whatever we have spoken today, that is why we had to fix H naught equals 1 and why we are running into this inverses. I mean, in fact, this kind of called inverses actually C1 star and 1 over C1 star, and you will run into the situation with moving average models of order 2, order 3, does not matter. While if you have one solution, the other solution is an inverse. In spectral factorization, when we learn the result, we will see that whatever we are doing in the time domain here to estimate the parameters actually amounts to factorizing the spectral density. Spectral density at any frequency is a number. If you are looking at a univariate time series, gamma of omega is just a number. It amounts to factorizing that number at each omega into a product of factors. Although you may not see that here at all, when we go through frequency domain analysis and all the wonderful things that come with it, then we will realize that the spectral density actually is being factorized behind the scenes as we are working with the ACFs here. And it does not, it is a very simple thing to know that factorizing a number into a product of two numbers is not unique. Okay. So, that non uniqueness is what is also being reflected here and vice versa. So, that is the point.